This question can be solved by at least two different methods. The first method that we will see is a rather mechanical method, while the second method which we will see is a more creative method. Since this question is about a cylindrical capacitor, it is worthwhile revising two important formulae connected with this type of capacitor. So here in this figure I have shown such a cylindrical capacitor, and of course this thing which you see over here is a solid conducting cylinder. It could be hollow, of course, it need not be solid, it doesn't really matter, and this radius is given to be A. Similarly, this thing which you see on the outside is a hollow cylindrical shell, which of course is also a conductor, and the radius, the inner radius of that particular shell, this we are going to assume that it's B, and finally the length of the capacitor is equal to L. Now if this L is much larger than both B and A, then the result that will be approximately true, and we have already derived it in the class, is that the capacitance of this cylindrical capacitor will be given by 2 pi epsilon naught L divided by ln B divided by A. And the second result, of course, is related to the electric field which is present in the gap of the cylindrical capacitor. So that result is better seen in the top view of the capacitor. So this over here is the inner solid cylinder, and this thing which we have shown over here is the outer cylindrical shell, and of course this radius we know to be A, while this radius is known to be B. Now assuming that the inner cylinder is positively charged and it carries a charge of plus Q, and the outer cylinder carries a charge of minus Q, of course we know that the minus Q will reside entirely on the inner surface of this shell, whereas plus Q will reside entirely on the outer surface of the inner solid cylinder. Then we know that the electric field goes from the inner cylinder to the outer, and it's symmetrical. It's going to be radially outwards. In this case it's going from the positive plate to the negative plate like this, and of course we know that the electric field decreases as we go out in the gap, because the electric field lines, they appear to be less dense over here as compared to over here. And specifically we can prove, and we have proved using Gauss's law, that the electric field at a point in the gap which is at a distance r from the axis of the cylinders is given by E equals Q upon 2 pi epsilon naught multiplied by L multiplied by R. That's the magnitude of the electric field, and in this particular case the direction will be radially outwards. It's pretty clear, because of the presence of R in the denominator here, that E decreases with R, and that is what we have said in the beginning, that as you go outwards in the gap the magnitude of the electric field decreases. Now let's keep these two equations over here for our reference, and let us turn to the actual question. Here once again I have shown the top view of the capacitor, and this distance is of course A, the inner radius, or rather the radius of the inner cylinder, and this radius is B, corresponding to the outer shell. And now according to the question I have to draw an imaginary cylinder which is coaxial with these two cylinders, but whose radius is the geometric mean of A and B. So the radius of the cylinder I am going to draw is root AB. So that's exactly what I've done in this picture here. This dark blue cylinder which you see is the imaginary cylinder whose radius is root AB, which is coaxial with the remaining two cylinders. Now as you know, wherever there is an electrical field there is associated with it electrostatic energy, and the energy density is given by U is equal to half times epsilon naught times the electric field magnitude square, where the electric field is presumed to be in vacuum, and therefore I have epsilon naught and not k times epsilon naught. Naturally, that means that in this gap where there is actually an electrical field, you have an electrical energy, an electrostatic field energy, which is given by integral the energy density, which is U times d volume, where d volume would be a small elemental volume of the gap. So the total energy present in the gap would be integral half epsilon naught E square times d volume. Now clearly there is no electrostatic energy in the body of the cylinders, because the field is equal to 0. That is, in this region the field energy is equal to 0, and so also in this region it is equal to 0. In fact, the electrostatic field is 0 in the exterior of the capacitor also in this region, and so the field energy there too must be 0. The only place where electrostatic energy is present is of course this region, which is the region of the gap, and this gap, which is the region containing the energy, is divided by our imaginary cylinder into two volumes. One of them is this one, the inner volume, and the second volume is the remaining one, the outer volume, that is this volume. Now this particular integral will give us the total energy contained in a volume V. If this volume is the entire volume of the gap, which includes the orange region and the green region, then what we get is the total energy in the gap, and that is the equation which I have written over here in the second line. On the other hand, if I evaluate this integral over the inner region, that is the region which is shaded in orange, the inner volume, then what I must get is the energy which is present in the inner region, the orange region. And what the question basically asks me to do is to prove that this energy, the energy in the inner region, is precisely half of the total energy in the entire gap. And one way to prove this result would be to actually evaluate these two integrals separately and to prove that this integral is half of this integral. And let's imagine solving the first integral. Clearly we substitute the value of E from this equation over here, and the term d volume would be the volume which is enclosed, this volume which is enclosed between two imaginary cylinders, one of radius r and the other one, the outer one, of radius r plus dr, where r is a variable, and of course this is the length of the cylinder, which is L, and clearly this volume would be 2 pi r multiplied by L multiplied by dr. Since we are integrating over the total volume, the limits of the integration would be r equal to a would be the lower limit, r equal to b would be the upper limit. So that in short is the way to find the total energy in the gap. Next we evaluate the energy in the inner region. Since we evaluate this integral in the inner volume, the limits of integration are now going to be r equal to a, and the upper limit would be r equal to, now we have to put here the radius of the blue cylinder which I've drawn in the original figure. In other words, we want to put this radius as the upper limit, which we know to be root of AB. So we write here root AB as the upper limit. We evaluate this integral, and after evaluating it, we are able to prove that it is half of this integral. There is, however, a second method which is more creative than the first method, which is probably a more mechanical method. Now, in this second method, instead of using an imaginary cylinder of radius root of AB, we actually assume that we have inserted a physical cylindrical conducting shell. So this is the shell, and the shell is supposed to be very, very thin. Now onto the inner cylinder, you deposit the same charge, that is plus Q, as in the previous method, and likewise you deposit the same charge minus Q on the outermost shell as in the previous question. Now by Gauss's law, we have proved a number of things previously. The first thing is this charge plus Q will reside entirely on the outer surface of this particular cylinder. Secondly, on the inner surface of the intermediate cylindrical shell, you will get an induced charge of minus Q. Thirdly, on the outer surface of the intermediate cylindrical shell, you get a charge of plus Q. And lastly, this externally deposited charge of minus Q will go entirely to the inner surface of the outermost shell. Now once again observe, like in the previous method, the gap is divided into two regions. One of them is this region and the second one is this region. But the difference in this method is that the division of the gap is now accomplished by a physical conducting shell rather than an imaginary cylinder. One can also view this as a series arrangement of two capacitors. One capacitor is between the innermost cylinder and the intermediate cylindrical shell, while the second capacitor is between the intermediate cylinder and the outermost cylindrical shell. Now we will proceed to prove that the electric field in this region is the same as the electric field which existed in that region when this intermediate cylindrical shell was absent, and the only charges which were present were plus Q on the inner cylinder and minus Q on the outermost cylinder. Clearly, the electric field in the gap that we are talking about will be in the radially outward direction, like this. And we can prove by Gauss's law that there is no net contribution towards this particular field by this charge minus Q, which is on this surface, and this charge plus Q, which is on this surface, and also by this charge minus Q, which is on this surface, because a uniform cylinder of charge which is infinitely long produces a zero field in the interior. We can of course find the field in the gap using Gauss's law, and we realize after doing that the field only depends mathematically, that is, on the charge which is present on this surface, and the magnitude of this field is actually given by Q upon 2 pi epsilon naught L R, which is provable by Gauss's law. And this charge Q is of course the charge Q present on the outer surface of the innermost cylinder. Clearly, it is the same electric field which was present in this region when the intermediate cylinder was altogether absent and the only charges present were plus Q on the innermost cylinder and minus Q on the outermost cylindrical shell, which means that the insertion of this particular cylinder does not really alter the field in this region. Likewise, we can prove that after the intermediate cylinder is inserted, the field in the second gap is once again radially outwards, like that. And by Gauss's law we can prove very easily that the magnitude of this field is given by this equation, which means that the electric field in this particular region has not changed by the introduction of the intermediate cylinder. So to summarize, in the original problem there are only two charges which are present. One of them is this plus Q, which resides on the outer surface of this cylinder, and the second is minus Q, which resides on the inner surface of this cylindrical shell. The intermediate cylinder is completely absent, and there is a continuous cavity or a continuous gap between this surface and this surface, and the field in the gap is radially outwards, like that, and its magnitude is given by this equation. Then we saw that when there is a thin conducting cylinder placed in the gap like this as shown, there is an induced charge on the outer surface of that cylinder which is plus Q, and similarly an induced charge of minus Q appears on the inner surface of that conductor, and otherwise the charge distribution, that is these two charges and the way that they are distributed, that remains the same. And we also saw that the electric field in this region and the electric field in this region do not change upon insertion of this metallic cylinder. Now the electrostatic field energy in a certain region in space is given by this formula, and from the analysis which has just been done, it is clear that the electrostatic field energy in this region is the same irrespective of whether this particular metallic cylinder is present or absent, because the presence or absence of this cylinder doesn't affect the value of the field in this region. And similarly, the electrostatic field energy in this region is the same irrespective of whether this metallic cylinder is present or absent. Finally, the cylinder itself occupies some volume, but this volume tends to 0 because the thickness of the cylinder is extremely small, and hence the electrostatic field energy in that particular volume tends to 0 before the cylinder was introduced, while after introducing the cylinder, the energy which is contained in that particular volume is actually equal to 0, because the electric field in the interior of a solid conductor is equal to 0 under conditions of electrostatic equilibrium. Now this essentially means that the introduction of this metallic cylinder has not affected the distribution of energy in the gap in any way whatsoever. So just to recall our original problem, we were given a cylinder of radius A which was made of a conductor and it carried a charge of plus Q. Similarly, we were given a coaxial conducting cylindrical shell whose inner radius was equal to B and which carried a charge of minus Q on its inner side, and we drew an imaginary coaxial cylinder of radius root of AB, and we wanted to show that the electrostatic energy in this region is exactly 1/2 times the total electrostatic energy in the entire gap. So we can first find the total electrostatic energy in the entire gap by referring to the same diagram, the original diagram, and then using the formula U equals half Q square upon C. So we get U, of course we are talking about the total energy, so we write the suffix total, equals Q square by 2 multiplied by 1 upon C. Now 1 upon C would be the reciprocal of this particular expression, and so I write ln B by A in the numerator and divide that by 2 pi epsilon naught L. So I'll just clear the screen by removing some of the currently unwanted things like this formula over here, and I'll move the total energy formula somewhere over here. We will now proceed to find the electrostatic energy which is contained in this region, and we have proved this earlier to be equal to the electrostatic energy which is contained in this region, which in turn is the electrostatic energy in the gap between the plates of a cylindrical capacitor. The two cylinders which make up the capacitor have radii A and root of AB, and hence the energy, which I'll call E inner because it corresponds to the inner volume of the gap in the original diagram. So U inner will once again be given by the formula half Q square upon C, but now in this case this C is not the total capacitance, but in fact it is the capacitance between this plate and this plate, so I'll call it C dash. It's going to be Q square upon 2 multiplied by 1 upon C dash, which is Q square upon 2 multiplied by the reciprocal of C dash. I'll once again use this formula, so I have ln, now this B, which is the inner radius of the outer cylinder, is now going to be root of AB. So I have ln of root of AB divided by the inner cylinder's radius is still A, and divided by 2 pi epsilon naught, the length of the capacitor is still L. So all you have to do now is to divide this particular expression, which is U inner, by the expression for U total, and using normal rules of algebra prove that the answer is 1 by 2.